all of the mass of the black hole is located in the very center in a region of infinitely small size and therefore infinitely large density. We call that a singularity.
Hello everyone, and welcome to Watch, a night with the Space Nobelists. During the past 10 years, several Nobel Prizes in physics have been awarded to scientists studying the physics and the secrets of our universe. To celebrate this, the Finnish Physical Society has created this new series, A Night with the Space Nobelists, that you are now watching. My name is Tommi Tenkanen, and I am the host of this series. I'm a cosmologist, which means that I also study the physics of our universe. The series will consist of 3 exciting interviews with recent Nobel laureates. In addition to this, we will also have a 4th episode where top Finnish space researchers will discuss the science behind the Nobel Prizes, as well as the role of Nobel Prize in general. Now, without further ado, let me present you our very first guest, Professor Reinhard Genzel. Professor Genzel is a co-director of the Max Planck Institute for Extraterrestrial Physics, a professor at the Ludwig Maximilian University in Munich, Germany, and an emeritus professor in the University of California, Berkeley in the US. He received the 2020 Nobel Prize in Physics, together with Andrea Ghez, for the discovery of a supermassive compact object located at the center of our galaxy. Hello, Professor Genzel. How are you?
Oh, hello. Very well.
Welcome to A Night with the Space Nobelists. We are really glad and honored to have you with us today. Before we begin, let me congratulate you for the recent Nobel Prize of yours. It is a truly remarkable achievement.
Thank you.
So you received your Nobel Prize for the discovery of a supermassive compact object located at the center of our galaxy. Do we know what this supermassive compact object is?
Yeah, it's with great probability it's a black hole. The reason the Nobel Foundation people did not go that step is because, as you know, research of that type, really can only prove things to a certain extent. We cannot travel there, right? So we have to make do with what we can see, and we can, from that, conclude that as long as general relativity, which is the theory of space-time invented 100 years ago, is correct, well then that object which we are seeing there influencing the environment of the galactic center must be a black hole.
Right. And not only a black hole, but a supermassive black hole. So can you elaborate a little bit on that? How big is this black hole?
Well, okay, I mean, black holes, I should say, from a theory point of view, again, general relativity, can have any mass, okay? In the universe currently, we have now evidence for generally 2 types of ranges of masses of black holes. One we call stellar black holes, which with some likelihood are the end products of massive stars, which at the end of their lives explode as so-called supernovae. And then they don't have any energy to produce anymore through fusion, and then they collapse, and the ashes then form an object which, a very compact object of a few kilometers in size, and that is a stellar black hole. The objects one calls massive or supermassive black holes are very different. They have masses between millions to about 10 billion times the mass of the sun. And so far as we know this, they all are in the centers of Milky Ways. So to speak, the central point, the central region of Milky Ways.
And how did they end up there? Why are they located at the centers of galaxies?
Right. I mean, okay, you have to basically feed black holes. They wouldn't start with that mass. And our current idea how that happens is that in the expanding universe, which exploded in the Big Bang 13.7 billion years ago, after a while, local overdensities of matter, mostly dark matter, but then also normal baryonic matter, recollapsed and then formed the first galaxies. We can see these objects nowadays to about a few 100 million years or a billion years after the Big Bang. That's the first objects. And we think that already at that time, in their centers, which are the sort of the central regions where the densest material is, it was likely that there perhaps very small massive black holes or clusters of stars which then collapsed to a sort of a small massive black holes formed. So you can imagine these were objects of hundreds to a few thousand solar masses. So that was a billion years after the Big Bang, and then followed a history where ever more material came into the galaxy. The galaxy grew, the host galaxy grew, and some fraction of the material which falls into the host galaxy through various processes, which we don't all understand in detail these days, then ended up in the central region. And there, the growing black hole, so to speak, became ever more powerful because it dominated the gravitation in the central region. And much of the gases which come in there, for instance, gas clouds, then end up in the end in such a black hole. And so by the time of about 10 billion years ago, which is when most of the galaxies actually formed, these very massive black holes existed. And we believe in almost every galaxy.
So if it is not very bright, how did you find this supermassive black hole that is located at the center of our own galaxy?
Think of the solar system. You have the sun in the middle, and the planets are orbiting on almost circular orbits around the sun. Now, the sun dominates the solar system in mass by far. And that means that the orbits of the planets are basically dictated by gravity of the sun. And that leads to the so-called Kepler's laws, which is the innermost planets move faster than the outermost planets, okay? And these laws, if you like, is the solution, nowadays you would say the solution also in general relativity of the motions of test particles, in this case planets, around a mass. Now, if you switch off the light of the sun in your mind, nothing would change, okay? You would still see, if you would look from outside, you would still see the planets moving around a point. And from the motion and solving the equations, so to speak, you would have to conclude the same thing, which is that there is a mass of one solar mass at the center of our solar system. So you see, that's the idea. That's the idea. You can test whether there's an unseen mass, a black hole, by looking at the motions of objects in the vicinity. And so in the galactic center, what we do, we look at the motions of gas clouds and stars. And with ever better precision, I should say, because, you want to go as close as possible. The event horizon of the galactic center black hole, which has a mass of 4 million solar masses, is a little bigger than the sun. So it's a very compact region on scales of astronomy. And so in order to prove that something is a black hole, you really would have to go all the way, theoretically, you would have to go all the way to the event horizon.
So, Professor Genzel, can you tell us what exactly is an event horizon?
Well, basically, again, think of it in the following way. You have the sun. Let's take the sun as an example, or the Earth. Let's take the Earth. And we know we can shoot rockets from the Earth to interstellar space, so to speak, by accelerating the rocket to a certain speed. That's, in the case of Earth, 11 kilometers per second, or about 40,000 kilometers per hour, right? That's how fast the rocket has to be to leave the gravitational influence of the Earth. Now, if you make the Earth smaller, then gravity at the surface gets larger, even if you don't change the mass. So in your mind, you could compress the Earth to a size of 1 centimeter. And then you calculate what is the required speed for your rocket. And it turns out that's light, the speed of light. But we know empirically that the speed of light is the fastest thing there is. They cannot communicate faster than the speed of light. So that means if you look from the outside on that 1 centimeter diameter Earth, you wouldn't see it anymore, because there is a region within which the escape speed is faster than the speed of light.
And that's the event horizon.
And that's the event horizon, that's right. Now, so the prediction of general relativity in that sense is fairly straightforward. As soon as you know that the speed of light is the maximum speed, and as soon as you know that light particles see gravitation as well. There is another thing that the general relativity stipulates for a black hole, and that is more bizarre, if you like, and that is that all the mass of the black hole, don't think of the black hole as sort of filled with some gas or something like this. All of the mass of the black hole is located in the very center, in a region of infinitely small size and therefore infinitely large density. We call that a singularity. And that's really bizarre, because it follows directly from the fact that, again, as I told you, light cannot escape. If you turn this around and take your rocket inside of the black hole, okay, you lost now communication with the outside, but you also cannot stop anymore. General relativity tells you that in finite time, you'll end up in the center, and everything else does so too, and so that's why you end up in the singularity. Now here we go, and many people in physics, especially quantum theorists, feel that cannot be. Infinitely small, infinitely dense regions are unlikely to be correct. And so this is where, so to speak, the end of the classical theory of general relativity is probably reached. And many physicists are fiercely looking for an expansion, an extension of that general relativity, which then presumably would not have a singularity there, but a very small region where the masses are concentrated.
Now let me switch gears a little bit and ask you about your recent Nobel Prize, because you were awarded the Nobel Prize last year in 2020. Would you say, has it changed your life some way?
As undoubtedly every Nobel laureate would tell you, is from the minute, so to speak, you are known to be a Nobel laureate, the following things are happening. First of all, you are supposed to know things about a broader set of issues, and people are asking you about that. And so some of that, of course, is good, because it opens up a important channel of communication between the scientific community and those people who are interested in research. And it's very, very important in our societies that people are interested in research, in physics, chemistry, etc., because of course our technologies and our lives depends on it. And so by allowing us to play, sometimes we come up with technologies which are useful to human mankind. So that's the communicator role. Of course, I give a lot of talks. Now, many Nobel laureates have told me, "Oh my God, of course, when you get once you get the announcement, then you don't do anything but travel." That one did not happen, of course. So, in a sense, I've been in a situation where I stayed here in Munich, including when it was the award ceremony was here in Munich and not in Stockholm.
So you shared your Nobel Prize with your colleague Andrea Ghez, who can be called your competitor. What would you say the role of competition is in doing science?
Yeah, well, okay. I mean, the scientific principle already tells you the rules of the game. The scientific principle is that you can make a statement or write that down a theory and say there are things called black holes and they work in the following way, and then you write down an equation, very much like what Albert Einstein did. But that doesn't mean anything until you can test these theories if they have predictions, and you can test them, but not only you, but also others. And something is considered to be a scientific truth in the sense of not fake news, but really something which everyone can accept, is if several groups find similar things, especially if they are based or they're basically targeting some very important questions, like in this case, do these black holes, which after all were predicted by theory of Einstein already 100 years ago. Carl Schwarzschild's solution is now 104 years old. So it's in that sense very important to test then these predictions and to test them by several groups. Of course, competition is one thing we need in science. Collaboration is also one, let me say, because sometimes the research difficulties are such that you cannot do the research by yourself. And in fact, in astronomy nowadays, very much like in particle physics, we are in a situation that the telescopes we are building and using and improving and so forth, and the instrumentation we are building is so complex that a single group or university or even country cannot possibly do it. So in our case, we very much profited from the European collaboration in astronomy through the ground-based telescopes of the European Southern Observatory, but also from the European Space Agency. That's a very important aspect, which in fact for Europe has been a decisive factor, I would say, in my field, certainly in my field, over the last years to get on par with the United States, which of course is a so much bigger country, powerful country. So the Europeans have been able to compete by collaborating.
Next, I would like to ask you a few questions that our audience has suggested. First, 4-year-old Levi is asking, how do stars explode? I guess this is very much related to how black holes form, isn't it?
Yeah, well, okay, so explosions. Explosions means you have to dump into the object lots of energy, which then means that gravity cannot keep the object together, which usually would be sort of the thing which makes everything stable. So in stars, that can happen if you have extra sources of energy in the outer surfaces, for instance, or you're using a new fusion material, etc., which produces more effectively radiation. Also, it can be that as a star ages, it becomes a little more compact over time and then hotter. And when it becomes hotter, then the reactions which produce radiation speed up enormously fast. They're very strongly dependent on the temperature. And so then you can get an instability that the photons which are being produced basically have enough pressure that they rip the stars apart and then lead to an explosion. You can also do the reverse. You can let something fall onto the star, and then basically that heats up and in return explodes. And the same thing can happen in the galactic center. So it's just about the balance between radiation, temperature, and gravity.
Right. And does it always lead to the formation of a black hole?
No, not always. I mean, so in fact, it turns out that if you look at the fate of our sun, or likely fate of our sun, then it will not end up in a black hole. Why not? Because as it gets older, it'll be getting bigger, actually, very much bigger than it is now, also colder then. And then in the very end, when there's basically all the hydrogen transferred into helium, then it basically sort of starts indeed to shrink together and become a compact little star. But that will not collapse because there is enough pressure still in fact, it's a quantum mechanical pressure which keeps the star just stable, and it becomes sort of a blue dwarf system, and does not explode and become a black hole.
That's fascinating. Then next question is from a group of 9th graders from Pyhäselkä. They are asking, what is the black hole nearest to us? Where is it and how far away is it?
That's a question which I'm not sure I can answer precisely, because it's the nearest black hole to us is a stellar black hole, and I actually don't know where that might be. It probably is at a distance of a few hundred light years or so. So this is a small fraction of the Milky Way. So throughout the Milky Way, you have many stellar black holes. And then this one, as far as we know, a supermassive black hole. So the supermassive black holes are in the centers, and then the star formation forming very massive stars with these supernova explosions led then to a sort of a distribution of these stellar black holes. And I suspect it's a few hundred light years.
Black holes are often connected to time travel. Could they be used for that?
In the sense that time and clocks are affected by gravity, then yes. And we have been measuring this, in fact, in the galactic center. We've seen effects due to the gravity, which basically slow down the clocks, and exactly how general relativity would have predicted it, in fact. So in that sense, absolutely, you can make time travel. Of course, time travel in astronomy is actually something which we do all the time, believe it or not, because of the finite speed of light. So if we look out in space, as we do, to look at distant objects, then because of the finite speed of light, it took light a finite time to get to us, and always backwards. So we look at, when we see the galactic center, then what we see now actually happened 27,000 years ago. So that kind of time travel, because of the large spaces and the effect of gravity onto clocks, yes, that's absolutely the case. Now, the idea of traveling with a black hole into a black hole and then coming out the other hand is a purely mathematical construct, which, as an experimentalist, I have to tell you, I don't take very seriously, because even the theory which leads to that mathematical prediction admits that there cannot be any mass transport. It is a purely mathematical construct.
So there are no wormholes in the universe?
And there are no wormholes, likely, yes.
But we cannot say for sure, at least not yet.
We cannot say for sure, not yet. I mean, as I said, in the sense that general relativity is a very well-tested theory, and in the sense that if you forget for now the prediction that this solution, which was constructed to generate a wormhole does not break down as soon as you put any gram of material in there, then it's possibly, theoretically possible, I guess.
Right. Thank you, Professor Genzel. Now, let me ask you the one last question, which is that, do you have any tips you could give to young students who wanted to do research on black holes?
Well, it's very clear. Some people say that black holes and cosmology, actually, the Big Bang, are, so to speak, the biggest mysteries in the universe right now. And black holes, so to speak, are the atom of the 21st century, very much like atoms and nuclei were the core objects of the 20th century. So in that sense, yes. And if we could get to the quantum aspects of black holes, that would be sensational. We discussed how difficult that is, but this would be sensational. Likewise, to uncover the riddles of the Big Bang would be sensational. And we are making lots of progress. So to the young people, I would say, if you want to do astronomy or physics, that is one of the fields which very likely will hold many opportunities for you.
Thank you very much, Professor Genzel. It was a real pleasure and a great honor to have you with us today. Thank you.
Thank you very much for listening to me.
This was the first episode in the series A Night with the Space Nobelists. I hope you've enjoyed it. Thank you and see you next time.